Section 3.2, Properties of Determinants. We already started with those properties in the previous section. I restated them here on the screen. As you can see, a square matrix is invertible if and only if its determinant is not zero. The determinant of any square matrix is the same as the determinant of its transpose. Transpose means when we switch rows and columns. If two matrices are square matrices with the same size, then the determinant of their product is the product of their determinants. Property 4, if A is a square matrix n by n, then if B is the matrix obtained by permuting, like you switch rows, then the determinant will become negative. If B is the matrix obtained by multiplying one row of A by any scalar k, then the determinant of the new matrix is k times the determinant of the original matrix. If A has any row or column of zeros, then the determinant automatically will be 0 if you calculate it out. If two rows or columns of A are the same, then the determinant of A is also 0. Let's see how we apply these properties. So let's say if we are given a matrix like this, find this determinant: 6, 3, 9, 1, 0, negative 1, negative 3, 0, 4. What's this determinant? One thing, always when you have 3 by 3 or more, like larger, 4 by 4, 5 by 5, always look at the matrix, see if there is a way around it to make it simple for you. In this case, I looked at the first row. I noticed the first row is a multiple of 3, so you can take a 3 out, like you factor it out. You get 2, 1, and 3, and then keep everything else the same. Nothing can be done for the other ones. And then from there, it would be easier to use these numbers 2, 3, 2, 1, 3, rather than using 6, 3, 9, computational wise. And then you can finish it from there, as we did in the previous section. Now, another thing to see, let's look at if they ask us to calculate the determinant of this 3, 3, 2, 3, 3, 2, 3, 4, negative 3, negative 3, negative 4, negative 5. How do we calculate this? Well, of course, you can see the first row has a multiple of 3, so I can take a 3 out. So it's the reverse process of multiplying by a scalar. Here, factoring a scalar out. Now watch something interesting I'm gonna do. You may apply row operations to this. Means I'm gonna take this number, the pivot number, and clean the first column. So I multiply row 1 by negative 3 and add it to row 2. I multiply row 1 by negative 2 and add it to row 3. Do you see what I'm doing? Keep the 3 out. It's not gonna do anything for now. 1, 1, negative 1 stays the same. Negative 3 times 1, negative 3 added, you got 0. This one gives us 1. This gives us negative 1. Negative 2 by 1, negative 2 added to the last one is 0. Negative 2 added to this, negative 5, and negative 3. Now, and you will see in a minute why I'm doing this, I'm going to use this pivot to clean the row or the column right, the negative 5. So you do 5 row 2 added to row 3. And this will give us 3, 1, 0, 0, 1, 1, negative 1, negative 1. 5 times 1 is 5, added to this is 0. Negative 5 minus 3, negative 8. What do you notice now? What do we have? Do you notice something? This is
triangular matrix?
Yes, it's an upper triangular matrix. Since it's an upper triangular matrix, so this is an upper triangular matrix. Then its determinant, keep the 3 out. The determinant is simply, as we told you in the previous section, is the product of the entries on the main diagonal. So that gives us negative 24. Let's look at another example. Find determinant of A if A equals 2, 0, negative 6, negative 8, negative 3, 6, 15, negative 2, 1, 7, 4, 0, negative 4, 8, 24. Take a look at this matrix. I'll give you time to look at this. What I want you to do is use this entry to clean up this. Clean up the negative 6. Clean up means make it 0. So to do that, you take row 1 multiplied by 3 and add it to row 3. So that will make this 0. This will become 6, 7, 8, and the last row stays the same. Now what? What's the determinant of A? Notice, now by just doing this, I got 2 rows that are the same. So the determinant by the properties is 0. And let me go back to the question that one of you asked earlier. If we have two rows that are the same for 4 by 4 matrices, 1, 2, 3, 4, 5, 1, negative 1, 3. Notice what we can do to find the determinant. Although these two rows are the same, you can take row 1 multiplied by negative and add it to row 3. So row 1 stays the same. 5, 1, negative 1, 0, 0, 0, 0, 0, 5, 1, negative 1, 3. Notice now, when you calculate the determinant, it's going to be automatically 0. That answers the question from the previous section. You don't have to calculate all these determinant stuff. You reduce this to 3 by 3 and then 2 by 2 and then find it out. Eventually you're going to get 0, but it would be much easier to do it this way. Perform some row operations on it, and then you got one row that is all zeros, entry zeros. That tells us by the properties that the determinant automatically will be 0. Quick notes. First one, determinant of A inverse does not mean negative 1 determinant of A. It's not like it's log functions, you bring it down. It doesn't work out this way. We ask these questions as true or false sometimes. If the determinant of A is 0, remember we said matrix A is invertible if and only if the determinant is not 0. But if the determinant is 0, this doesn't mean that two rows or two columns are the same. Three, we told you that the determinant of A times B, if they have the same size, is the determinant of A times the determinant of B, right? I'm going to use this to look at what's the determinant of A to the 7th power. Like if they ask you, find the determinant of A to the 7th. Well, the way this works is you do determinant. A to the 7 means A times A times A 7 times. This would be the determinant of A times determinant of A times determinant of A times determinant of A 7 times. Okay, 7 times. And this can be rewritten as determinant of A to the 7th power. So in other words, if you're asked to determine or to find the determinant of A to the 7th, all you have to do is just find the determinant of A and raise the answer to the 7th power. Raise the answer to the 7th power. Next one, determinant of A plus B doesn't equal the determinant of A plus the determinant of B. For general case, means sometimes you can find two matrices that this works out, but not all the time. And to apply the properties of determinants even more, let me show more examples. Say the determinant of ABC, DEF, GHI is 10. Find GHI, DEF, ABC. Find this determinant. So what do you notice? Compare the given one with the new one. I found that row 1 and row 3 get swapped. So this means the answer is -10. Why? Based on one of the properties. If you swap two rows, the answer will be the opposite of the original one. Calculate the determinant of 3A, 3B, 3C, DEF, GHI. Calculate this determinant. And the next one. So again, we're calculating these parts based on the original. This is the original determinant given. So what happened for the second one? Comparing the original one with this one, they multiplied 3 times the original. The original had a determinant 10, so you multiply 3 by 10, 30. How about the next one? Anyone could see what happened? What's the answer to number 3? So what they did here, basically, to obtain this matrix, they they took row 2 and they added to row 1, right? To obtain this. So they took the original given determinant or matrix and they added row 2 to row 1. So we, after doing this, we got this. Now what does that tell us? What does that tell us? This tells us when we do row operation like this, the determinant stays the same. It's not going to affect it, right? Remember when we did this determinant here, if you calculate the determinant on this, or if you do row operations and then calculate the determinant, you will still get 0 regardless. Makes sense? So when we apply some row operations like this, the determinant stays the same. So this would stay 10. How about adding another one? How about if we have A, B, C, 5D plus A, 5C plus B, or no, 5E, 5F plus C, and this stays the same. Let's see, what's the determinant of this? Yes, good job. One person got it so far. How about the rest? Yes. Yeah, so what happened is these operation, you can drop it, is the same. So the determinant will stay the same if you drop the plus A plus B plus C. So basically what they did, they added row, they took row 1 added to row 2 right after they did the multiplication. So that process addition, you can drop it. So you get 5D, 5E, and 5F. And notice you can factor a 5 out. That will give us A, B, C, D, E, F, G, H, I. This one is given 10, so you get 5 times 10, which is 50. Any questions about these properties? As you practice more and more, you will get to memorize them. So that's what this section is about. Any questions about this? So in cases where you have, again, 4 by 4 or more, usually 3 by 3 or more matrices, and they ask you to determine the determinant, see what you want to do. Can you get 2 rows to be the same? Or can you get that matrix by doing some operations to get 1 row or 1 column to be 0? Or again, 2 rows or 2 columns the same. That will make it very easy for you. Or think about triangular matrices. Can you get it to be a triangular matrix? So triangular matrix. Or can you get it to be 2 rows, 2 identical rows or columns? Or can you get 0 row or 0 column? So that's something you can think about. Of course, you apply row operations to matrices, clean up columns. That would make it easier. So if you're asked to find a determinant for 4 by 4, and you go through the same process I showed you in the previous section, you have to do it first time, next time, next time. It's like, oh my God, that's a lot of work. So here in linear algebra, that's not what our goal to show you, to see if you can calculate determinants this way, but to see if you can think about making the determinant easier to calculate. That's the difference between if you learned this back in high school and nowadays, or at this level.